This is the fill plug for the transformer. It's an oil bath full of mineral oil. You got to fill this up at least to come over the top of the secondary here. You're gonna have an air bubble. You should have an air bubble in there anyway, so if you get any expansion, it doesn't want to. A little air bubble is not going to be a big deal. And here's the drain plug right here. So, you know, we can't ship it full of oil, so we'll do the drain oil out, and you'll have to fill it full of mineral oil as much as you can. You can see that this is very, very full. Okay. Alright, this is your high voltage output here. 2 white. Here's the input from the unit. So you're going to get a ground wire for your load and a piece of high voltage wire that goes to your load also. Right, and you'll have this little wiring harness right here. This is a safety gap. It's an over voltage shutdown. Alright, so you take the safety gap and it's Velcro. All you really got to do is stick the safety gap on that Velcro right there. Open up the harness. All the wires are color coded. It's pretty easy. Black to black. Twist out of it. Put the black in. Put the red in. Put the green in. Alright.
And what's that fourth green for?
That's your, it's your,
the ground?
Yep, it's a ground, yes, a ground for your load. Alright, so then you have this little short high voltage wire here, which can go either one of these. I put it there and there. Your high voltage out to your capacitive load, it's going to be a capacitive load.
Yep. Yes. And then you might make a mention on that wire there. The whole idea of the remote oil transformer is that in low capacitance loads, you want to get it as close to the load as possible. Right. So that wire can be shortened if necessary.
Yeah, this one here. Okay, now we're going to put our, this is our ground here. So this is the ground for the output of the transformer. Your ground and your high voltage are here and here. And we have this capacitive load that we made up.
A test load.
It's a test load, right? And we're going to connect this, and this is adjustable from, you know, 9 picofarads to 200 something picofarads. And we're going to put it about right about the A, which is at about 75 right there. Okay, so we're going to connect the ground, and it's irrelevant where this goes. Here, because this one moves. Right, I'm going to turn this around.
Ground goes to red, John?
It doesn't matter. It doesn't matter which side, you know, it's just because this one moves and this one's easy to move, we keep this one high voltage away from everything else. So we're going to turn this around, actually. Flop it over this tube right here. Now we put the ground on the moving side because it's easier than moving high voltage. It stays away from everything. Okay. We come around this direction. And then we have our little harness right here. And we got blue, green, black, and red. And it goes to the corresponding. This is your high voltage, black and red. This is your ground return from the spark gap. That's the over voltage. And you have a spare grounding lug right here for grounding whatever goes to the ground of the line cord.
Earth ground.
Yeah, earth ground, right?
Supplementary earth ground if they want it.
Okay, that's the connection for this. Very simple. Now the variac has 2 cords coming out of it. One goes into the variac and one comes out of the variac. These 2 outlets are separated. They're not together. So you can't swap these. These are color coded as long as you put the yellow with the yellow and the red with the red. You know, the power comes into the unit. Turn the switch on. It powers the variac through here. The variac varies up and down and comes back to the full bridge fit. So I'm we'll have to turn this around here. It's going to be a little tricky. We're going to unplug this right here real quick. What's this way? Like so.
Yeah, which definitely.
220 single phase AC with a ground. Now we don't know what you have for a plug. I have a spare one here somewhere. But we'll probably ship it to you with the end stripped in whatever receptacle you have. We don't know because we're so international it's ridiculous. We don't know who has what. So you may have to go to a hardware store and get whatever 220 single phase AC plug grounded. So we're going to drop this here. And we're going to catch our...
Sure. We got our connections in the back again.
Yep, just like they was. Okay. Well, here's our plug panel with the variac connected. And we have our transformer connected. And we have our capacitive load connected here. Let's tape on that. So this high voltage wire doesn't lay across anything else. It's not laying across the negative or anything. We made a modification. This is 220 single phase with this type of plug, just for testing purposes. Plug that in. Okay. All right, so we're going to make sure the variac is down.
The variac here supplies only the voltage to the power amplifier section of this particular unit here. It controls the voltage to this section, consequently the output. The voltage is read on a voltmeter here, and the amperage that is drawn from the power amplifier is read on this meter here.
Mm-hmm. No, that's fine. Yeah.
So
just get a little closer so
when
I can
you multiply the volts here and the rails there, it should give you your watts in power. So if you have 100 volts at 1 amp, there you go.
This is your frequency adjustment. It varies from
17 to 99.
17 to 99 kilohertz.
Right.
And the frequency then shows up on that meter on the left.
It's right here.
Okay.
Which we can.
And the frequency, yes. This is the duty cycle, which is necessary because when you hit some resonant loads, the Q is so high that it only takes a small amount of voltage to start drawing current at resonant.
Right. Which we can show right now.
Which we can show right now.
So we're going to turn up the voltage just a little bit. We're probably at 30 volts. And when we find that resonant peak, the current is going to go way up.
Wow.
Quite a bit. So we can turn this duty cycle down and find that resonant peak right there. So this resonant peak is at 30 kilohertz. Now if we had this duty cycle way up, the current would go up so high you wouldn't be able to have any volts. So it enables you to have some rail voltage and have control.
All right, now this amount of capacitance that this thing is resonated at was set by our test unit right here.
Right, which we can show.
Now this is also a type of a corona cell where if you look carefully between
these two coils here,
while it's running,
you can see the corona. I put it.
set that pretty close.
Kind of like that.
oh, yep.
Now John's going to put the power to it. Put some power to it, and you can actually hear the corona.
We're going to readjust for the. Let me turn this down here a little bit. We'll find a resonant frequency of that. We'll shut down here. Alright, so now our shutdown works good.
Now this particular load is shutting down mainly because the Q is so high on this capacitance.
Close this up a little bit. It's going to help us a little.
You might explain the...
Yeah, the reset. Now, okay, we have our safety gap, which you see it's shutting down our shutdown. We have to open that up a tiny bit. And you can probably explain how it saves the transformer.
Yeah, the idea of the safety gap across the transformer is that when you have a real high Q load, you're going to need very little voltage to get a resonant rise of a lot of current. Now, in order to get this current, the transformer has to put out a lot of voltage. And it's doing that at a very low input voltage. So if we did not have some protection across the transformer, it would be very easy to destroy it under certain loads.
Right, because with very little voltage, I mean, look at the current, it goes way, way up, and you have hardly any voltage.
Right. There's an example right there. Because the Q of this system is so high, there is no real power drawn from the system. It's all reactive power, and of course it's being canceled out at resonance. And this is why the applied voltage to this goes so high. It's referred to as resonant rise. So we have to compensate for that. And we compensate for that with the duty cycle control and, of course, with our shutdown circuit that safeguards the transformer should we overpower it.
So we can see that we are at our resonant peak right here.
Now, when John turns this up,
Right.
you can see he'll turn it up to a certain amount of current.
You could show that, okay, with a duty cycle.
Why don't you turn it up to 2 amps?
Yeah.
Now that's 2 amps, and the voltage here, what's the voltage on the variac
No,
now?
it's not even 25 yet.
It's 25 volts,
Less.
and the voltage isn't even measuring here.
Right, this way we can turn this duty cycle way down. And we can optimize.
Now you can turn your voltage up, and what you're hearing
You should be able to see it in there really good now.
that.
Should be super purple in there.
Well, I
Now
definitely.
it's shut down. It's shut down because the voltage on the transformer was too high. So right now we feel as though we can open up that gap a little bit more
The safety
to
gap.
give you a little bit more leeway.
Alright, so when it does happen, okay, it shuts down the signal to the amplifier circuit. So you have to turn your variac down. Now because there's such a large capacitor on the amplifier circuit, you have to drain that power off before you can reset. This button that says drain, you'll see that it's still holding this charge even though we have no voltage going into it. And it'll go through the transformer and out to 0. And then you get reset and your frequency comes back on. Your drive circuit is connected to your power circuit. And you can, and it'll probably shut down again, right? So you turn the variac off, get rid of your leftover voltage, reset the unit, and you're back to your resonant frequency.
Now the next sequence of videos are going to be, we're going to open up the gap, the safety gap a little. It is now set about, what?
Oh, a quarter inch or so.
We're going to set it up to,
It's only going to take a couple, maybe 2 or 3 turns on that screw.
yeah,
To make a big difference. Small adjustments, you know. If you're
Small
adjusting,
adjustments,
if you're adjusting for your load and you adjust it, just do small adjustments and let it reset until you get it to that point where that's where you want it to shut down.
now also the range of this unit right now, you see it's operating at 31 kilohertz and the load capacitance is about, what would you say, John?
75.
About 75 picofarads right now. So it's easy for you to calculate the inductance part of the complex equation where your inductance of the transformer is resonated with approximately 50 picofarads at 31 kilohertz. So knowing that, knowing those two factors, you can calculate your load capacitance, and if you happen to know your load capacitance, you can kind of calculate where the frequency of resonance will occur. Now, there are other factors that enter into the equation, which is going to be the resistive component of the load. Now, if you're familiar with complex notation, you will know that that is symbolized as R plus J X or L. Now, if X equals L, the J factor becomes 0, and the load now is just resistance. And this is what you want to accomplish, because this resistance will be determined, I should say, your output of corona will be determined by that resistance. And of course the settings of the unit. So there's a lot to play with, and there's a lot to probably refresh some of you engineers' minds on as far as complex notation of AC waves and all that good stuff. This for me was second year college level. So I guess the next thing is to adjust the spark gap a little wider, because we want to be able to give you a little bit more flexibility, and we suggest that you only play with that safety spark gap when you really get used to what's going on, because if you open that spark gap, you could destroy the transformer. Now the transformer is easy to replace, no problem, but why destroy it if you can prevent it? But it can be replaced.
Okay, we're going to readjust this safety gap here, which is fairly simple. I discharged, make sure there was no output there.
But where did you?
Off. Oh, just across this load right here.
Okay.
So, the nice thing about it being Velcroed and plugged in is that you can just take the spark gap off and pop the screws out of it real easy.
You'll notice that the spark gap is not designed to be constantly played with. And once you set it,
You shouldn't have to worry
hopefully
about it.
it'll remain in that position for your particular experiments.
I have to coax it out of there a little bit. So I really just pull the cover off here. I'm going to open this up. Let me get my little pliers. Okay, this is double nutted here, so you're going to want to hold the nut. I'm going to back it out a couple of turns. Tighten up the nut here. And we'll just lock that in with the other nut here.
I wouldn't put the 4 screws back in.
No, we'll just sit down because we might have to make a couple of adjustments here. So we can just set this back on here. Set it here. Put it back in and see what happens. Okay, so we want to.
Yeah, it might be a little bit too, about 9/16, right in between half-inch and 5/8.
Okay, so I'm going to start all over here again. Do a little bit of duty cycle so we can see the current.
You don't want
You Probably want to start out pretty low.
Put your thing
So we're going to bring the current up a little bit so you can see the current. And we can adjust this frequency, and you'll see a rise right there. There's the rise right there. That's, and it goes down when you go there, below it, and it goes down when you get past it.
See how it lines up.
Well, there's your resonant peak at 31.2 kilohertz.
1/16 of an inch is going to
Now we
be
can
a
turn
lot,
this duty
you know,
cycle
it
down.
makes things kind of close sometimes.
And we can give it some power.
Corona in there though.
You see it at all?
Yeah. But I don't know if that's is that straining the transformer too much.
It was putting out pretty good.
Yeah, so just a small adjustment. Would you take that back 2 turns?
Yeah, about 2.5, maybe 3 turns. Well, let's play it again.
Okay. You're gonna tighten it up by 1 turn?
Yeah, it's easier to tighten it up than it is to loosen it, actually.
Yeah.
Slide this off here.
Is that on now?
Yeah.
We have shown you a very conservative operational procedure that we used here. And once you get used to it, you might be able to open up the safety gap more yourselves and get a lot more power out of it, because the only thing you're really risking is the transformer, and that is a $100 bill.
That's nominal.
Yeah.
And you can...
Unless you found it,
It's shutting off at about 150 volts, and how many amps was that?
150 volts with 3 amps?
No, it wasn't even... right. 100 volts and about 1 amp.
So it's putting out into real power about 100 watts.
Which you can go up and up and up.
It can go obviously a lot higher.
Right. See, we're going to turn our duty cycle all the way up.
Yep.
We're at 38 kilohertz.
I'm going to show the arc without the resonant load connected, just the output of the transformer. And we're going to bring this up to about 250 volts.
That's about 500 watts. 500 watts of arc. We can go up higher,
But there's no need to, really.
but there's no need to really.
Okay. Now we're going to hook up our resonant load, right?
Now we're going to hook up the resonant load. Why am I repeating this?
I don't know.
There's an echo in here, echo in here, echo in here. Okay, so
Pretty good though.
Okay, now I can talk now, okay?
Oh yeah.
Now the resonant load is a test load consisting of our variable air capacitor that is variable out to,
200 picofarad to 13 picofarad.
now we're going to set the capacitor at about, I'm guesstimating about 150 picofarads. Now at 38 kilohertz, that's around the resonance point, across the capacitor we're putting a load of 260,000 ohms, which represents a Q of 10 approximately, with the capacitive reactance of about 2.6 megohms. Again, these are approximate figures of capacitive reactance.
You see the corona in there? In
Now-
that gap? Okay.
Now the variable capacitor is set with a space, and you will see the plasma between the plates of the capacitor. And you will also hear it because it's very loud, because it's switching with the duty cycle.
Okay, we're going to recheck our resonant peak here. We should see the current go up to a peak. It's right about there, 37 kilohertz.
Let's shut the lights off.
Yeah, maybe turn off the overhead lights. Yeah, I can see the blueness, but I'm not sure if the camera will pick it up. That's good.
Let's get drawing for power.
A little over 200 volts and about an amp and a half.
Now that was a current, that was a power draw of 300 watts from the machine. What you hear is the corona and plasma between the plates of the capacitor, which represents only about a small percentage, or about 10% of that 300 watts.
3/16 holes lined
The
up.
rest of the power is being dissipated in the resistive load connected across the
You'll see it.
capacitor. That's it.